All right, in this podcast, we're going to look at electroplating and Faraday's laws. Okay, so electroplating is just another example of an electrolytic cell. It's used to plate one metal over another conducting object. So, like silver over stainless steel, gold over copper or nickel, chromium over iron. Okay, so in order to electroplate, you only have one cell, okay? So you will have the metal ion that's in solution, okay? So you do need a solution of whatever metal you're trying to plate with. And then you need your anode to be made of that plating material or metal also. The cathode is going to contain whatever object you're going to plate. And then, of course, you need a source of current, such as a battery or something of that nature. All right, so only the metallic ions in the solution are going to be attracted to the cathode and are going to reduce onto it, plating it. The metal anode is going to oxidize, so lose electrons that are then going to be put into solution into the one cell, basically replacing the metal ions that were reduced onto the spoon in this particular case. So it allows the process to continue. Negative ions do not play a part in electroplating other than just maintaining the neutrality of the solution. All right, so in our hubcap example, our hubcap is definitely going to be the cathode. Our anode is going to be the chrome electrode. And then our oxidation is occurring at our anode. And our reduction is occurring at our cathode, which is our hubcap. So our half reactions are up here. Hopefully you notice that they're basically just the opposites of one another. Okay, so here is the oxidation reaction, and here is the reduction reaction. All right, so here we have some aluminum glasses. We want to frame them or plate them with gold. You see we have the gold electrode. That is definitely the anode. And then we have the material we're trying to plate onto. That is the cathode. And then we have a gold nitrate solution. So we also have little gold ions floating around in solution. Okay, so the oxidation reaction is occurring over here on the anode. These guys, these golds, are losing electrons. So they're losing one electron. And then the reduction is when we're actually taking those gold ions that are in solution and we are gaining them and becoming the gold metal, which is plating onto the aluminum frame. Okay, so Faraday's law allows us to look at a couple different things about redox reactions. So they allow us to determine the stoichiometry of the redox reaction that is occurring in the electrochemical cell with respect to the number of electrons transferred, mass of material posited or removed from an electrode, the current, the time elapsed, and the charge of the ionic species. So in order to do this, you need to know a little bit about current. So current is abbreviated I. It's basically the amount of charge that's going to pass through the cross-sectional area of the wire per second, or the medium, which could also be your aqueous solution. Okay, so the formula for current is equal to Q over T, where Q is our charge in coulombs, which is abbreviated capital C, and time is T, and that's in seconds. We also have Faraday's constant, which we're going to use. You've used it previously in the delta G equation. We're going to revisit it again. Just understand that 1 Faraday is equal to Faraday's constant, which is how many coulombs we have per moles of electrons. All right, here's a other couple of little useful info things that you may or may not need later on. All right, so an example. So how much charge passes through the cross section of a wire that is carrying 0.98 amps? So that is our current for 12.3 minutes. So that is our time. Okay, now our time needs to be in seconds. So that's the first thing I need to do is I need to convert it to seconds. So basically I'm just multiplying it by 60. And when I multiply it by 60, I am getting 738 seconds. Okay, now I have my equation. I equals Q over T. My I is 0.987. I'm looking for my Q. And my T is 738. Cross multiply. And my charge is 728.41 coulombs. Okay, so that's the first part. All right, now it wants to know how many moles of electrons pass through the cross section. So let me erase some of my work here so we've got some room because I like to write big. All right, I think that's from all my years of having to write big on the board as a teacher because I don't remember writing big when I was younger, but anyways. Okay, so I know that I have 728.41 coulombs, and I know that 96,485 coulombs is equal to 1 mole of electrons. Okay, so I can use Faraday's constant to help me determine how many moles of electrons I have. So if I solve that, I get 7.5 times 10, to the negative third moles of electrons. Minutes. All right, in this question, we are asked how long it would take, so we're looking for time, to plate out 3.5 grams of silver from a aqueous silver solution that has a current of 2.5 amps. Okay, so first thing I need to do is I need to figure out what I do have here, okay? So I do have my current, so I have my I. I'm looking for time, which means in my equation, I need Q, I need the charge. So you can go from grams of silver to the charge. So first I'm going to put my molar mass down here. And that is for my silver. And for every 1 mole of silver, I am getting 1 mole of electrons because I'm only gaining or losing 1 electron. And then I know that 1 mole of electrons is equal to 96,485 coulombs. All right, multiply, divide, and I got that we have 3,131 coulombs. Okay, now I'm going to plug this into my I equals Q over T equation. So I've got 2.5 is equal to, got my charge over my time. All right, cross multiply and divide. And my time ends up being, let's see, 1,252 seconds. I don't know about you, but I have no idea what that actually means, so I'm going to convert it. Okay, there we go. And 1 minute. Okay, so I divide, and I got 20.9 minutes, which is definitely something I can understand. Okay, if 2 Faradays of electric charge pass through a silver nitrate solution, what mass of silver is plated out? Okay, so we got 2 Faradays, and we've got 1 Faraday is equal to 9,485 coulombs, and I know that 9,485 coulombs is equal to 1 mole of electrons. And I know because it's silver, it's only going to be a 1 plus. So I know every 1 mole of electron is equivalent to 1 mole of silver. And then I need to get to my mass. So 1 mole of silver. And then I need the molar mass of my silver. Multiply, divide. And let's see, I got 215.74 grams of the silver. Okay, so in this particular one, we've got a power supply hooked up to 2 platinum electrodes. We've got a copper sulfate solution in there. And we know that copper metal is going to be deposited on one electrode, and the oxygen is being produced on the other electrode. And it gives us our 2 reduction half reactions. And first thing it wants is for us to indicate the direction of electron flow. Okay, well, you'll notice this is definitely going to be the cathode here. Okay, this is where our reduction of the copper ions is going on. So electrons are definitely flowing that way towards the cathode. They go from anode to cathode. Okay, and our balanced equation, so we have the Cu2 plus and the 2 electrons making the copper solid. And then this equation has to be reversed. So we got our 2H2O makes oxygen gas, 4 hydrogen ions, and 4 electrons. Okay, our atoms are balanced, but our charges aren't. So we're going to have to multiply this one by 2. Okay, all right, now we can cancel our electrons and write our final equation. So 2Cu2, Cu plus 2, oh, and this was a 2 plus. My bad, guys. Watch for the details, right? Because I just screwed that one up. All right, 2 H2Os, and not sure why I wrote a plus sign there. Okay, and that is making the 2 coppers, the 1 oxygen, and the 4 H pluses. So hopefully you realize that this solution is going to get more acidic as we go along. All right, so it wants us to predict the algebraic sign of delta G. Okay, so just based off the fact that the only way we can do this is with a power supply, I'm saying that delta G is definitely going to be positive here because it's non-spontaneous. We have to force it to happen. Okay, now to calculate our value for delta G, we're going to use our delta G equals negative N E cell. From the previous slide, hopefully you remembered we had 4 electrons when we balanced our redox equation. Faraday's constant, and now I've got to find my E cell. So this is the reduction, nothing to do with this one. All right, but this is my oxidation, so I have to flip my sign. So I have negative 1.23 plus 0.34, which gives me negative 0.89. Okay, so that negative 0.89 goes there, and then I multiply across, and my delta G ends up being 343,487 joules per mole. Okay, so continuing with the same cell, we've got an electric current going through it, 1.5 amps. Going for 40 minutes, okay? So we got current and we got time, and it wants to know, down here in the actual question part, wants to know the mass of the solid that is deposited, or the copper that is deposited onto the electrode. All right, so first off, you got to get your charge. In order to do that, you've got to plug it into I equals Q over T, but T needs to be in seconds, not minutes. So I'm going to get it out of seconds here. Out of minutes, excuse me, into seconds. So that's going to give us 2,400 seconds. Okay, so now if I were to use I equals Q over T, I have 1.5 amps for my I, looking for my Q, and my T is 2400, which gives me a charge of 3600. So I got 3600 coulombs here. Okay, and I got to get my coulombs to my mass of my copper. All right, so I got coulombs equation, which is equal to 1 mole of electrons. Okay, now, if you remember from our balanced redox equation on the other side, we were definitely dealing with 4 moles of electrons, and every 4 moles of electrons was giving me 2 moles of my copper. All right, and then next step, all right, erasing a little bit of this so it doesn't run all together. All right, is for me to get 2 grams of my copper. So I know that my molar mass of copper is 63.55 grams. Okay, so multiply, divide, and you get 1.19 grams of copper. All right, lastly, we need to calculate the dry volume in liters, measured at 25 Celsius and 1.16 atmospheres of the O2 that is produced. Okay, so if I know that I have this much copper, I can determine how many moles of oxygen I have. Okay, so first I'm going to get my conversions going here. So I'm getting out of grams into moles. All right, and then I'm going to look at my mole-mole ratio for my balanced equation. Looks like I had 2 moles of copper for every 1 mole of O2, which gives me 9.3 times 10 to the negative 3 moles of O2. And I'm going to erase again so I can write up here. All right, and then I can use, this is not standard conditions here, okay? So 25, 1.16 atmospheres, but it is a gas, so that means PV equal nRT. So pressure is 1.16. V is what I'm looking for. Number of moles I just found were the 9.3 times 10 to the negative third. My R is 0.08206. And my T is 25 Celsius, convert it to Kelvin, so 298. All right, multiply, divide, and I got that I have 1.197 liters of O2. Okay, so in this one, we've got these 4 substances, these 4 ions. They're all in a beaker. We've got 2 platinum electrodes. We've got a power source hooked up. And we're going to try to see which metals are going to plate out. So first off, we need to know the direction of electron flow. So electrons always flow from negative to positive. Okay, so what that means is, all right, so that means our electrons have to be going out of the negative and then towards the positive, okay? So coming out of here, going towards the positive part of the battery, coming out of the negative part of the battery. Okay. Then we need to identify the metal that plates out. Well, in order to do that, you sort of need some more information. So you would need to know the standard reduction potential for those 4 ions. Okay, so for barium, it is, okay, negative 2.9. All right, that's my barium, Ba. Okay, let's change colors so you can see that a little better. All right, my copper is negative 2.87, so that's my copper. And then my lead is negative 0.13. And then my strontium, oops, wrote it in the wrong spot. Okay, my strontium is going to be negative 0.289. Okay, so the metal that is plating out means it is being reduced. Okay, so for it to be reduced, it needs to have the most positive value, reduction value. So that means lead is the one that's going to plate out.